What is mass? Well, good question. So we go back to the early times, right, long before our understanding of gravity. The concept of mass and weight would have been synonymous. It was simply something's heavier or lighter than another object. And even today, there's still confusion between mass and weight. Simply put, mass is the amount of matter in an object. Weight, however, is the force exerted on that object by gravity. And that became apparent by the 1600s when Isaac Newton related forces to mass. His second law states that the force of an object is related to mass and acceleration. And gravity is an acceleration, and hence the force, which becomes known as weight. But Newton also had another very important discovery relating the force of two objects. Two objects are related by both of their masses and also their distance, and that's the force of gravity. By the 1900s, Albert Einstein related energy to mass. And I think everyone knows this equation. It's his famous E equals mc squared equation, but it simply states that energy of an object is related to mass and the speed of light. It's actually the speed of light squared. All right, Mr. Einstein, that seems a little bit strange. Why is a wave speed in this equation? Right? C is the speed of light. And the speed of light is the speed at which waves travel. Why is it there? Well, let's hit some properties of mass first. Right? Mass can change. Now, Einstein's complete equation describes relativistic mass, and that's the ability for an object to gain mass. And we don't really see it today because it's hardly noticeable until you reach speeds that are closer to the speed of light. This example that you see there, something that's maybe 10 kilograms, is 100 kilograms as you get very, very close to the speed of light, 10 times. And energy can never be created or destroyed, but mass can be. A massless photon can hit empty space and two particles are created, and these particles have mass. It's a process known as pair production. Similarly, matter and antimatter can annihilate. So here's mass being destroyed. Now, two photons are created, so energy is always equal, but mass is destroyed. And the same process happens in an atomic nucleus and nuclear energy. All right, so let's get to a new explanation then for mass. Mass is standing wave energy without consideration of wave speed. That's c in the equation. Now, a particle is made up of standing waves, but beyond it, it is traveling waves. And to see what a standing wave would look like, here in the center, that's stored energy. It's not moving. A standing wave is a stationary wave. And this would explain why mass is energy and also why wave speed is in Einstein's equation. But there's more. Right here you see a better illustration now of what creates that standing wave. And a standing wave could be a reflection. It's essentially two opposite waves of the same frequency. But imagine two waves, an in wave traveling at the speed of c and an out wave traveling at the speed of light c. Now, a property of waves is when something is in motion, it experiences a principle known as the Doppler effect. The wavelength changes. Wavelength changes and it affects now what's within that standing wave energy, which is measured as mass. So that can account for relativistic mass. Now waves also have another principle of superposition. And this can account for the creation and destruction of mass. And here you see two different waves. If they're in phase and you add their amplitudes together and you get the result there. Well, you see the bottom left. Now something that would be out of phase, completely opposite, would be destructive. You see no amplitude. That's known as wave interference. And essentially it's the resultant wave amplitude is the sum of two or more waves. And so two particles of opposite phase would look like this. They'd be destructive. Their standing waves would collapse after annihilation and you wouldn't be able to detect them. There would be no wave amplitude. Standing waves have completely collapsed. But imagine a photon coming along with enough energy. right? That energy now causes kinetic energy, motion of those particles. Once they separate now, those waves that are reflecting are standing waves again. And so all of a sudden we can measure that mass once again. Those particles were still there, but now they can actually be seen as mass. So mass and its peculiar properties, right? Being constructive, disappearing, relativistic mass, can all be explained by particles that consist of standing waves. Particle motion and the influence of other particles changes this behavior of waves, affecting the mass. And that's it for today. Have a good one.